All right, so we are going to be talking about something called electron configurations and electron configurations with orbital diagrams. We need to talk, when we write electron configurations or when we draw electron configurations, they're always based on following these three ideas. So one of the ideas is something that is referred to as the off-bow principle. The off-bow principle states that electrons will fill the lowest energy level orbitals first. And then the next one says if two electrons are in the same orbital, they will have opposite spins, and we call that the Pauli exclusion principle. This. Okay. And then lastly, we have something that we refer to as Hund's rule, which says within each shape, there must be an electron in each orientation before a second electron can be added. Okay? Now, yes?
So for Hund's rule, you can't, well, does it mean like you can't add two at the same time?
Sort of. We'll do it. We'll go through it. Now, on your desk, you should see something that looks like this. Yes or no?
Yes.
If you do not have one, let me come give you one.
Wait, never mind.
Okay. All right. So what this is an aid. It is a helper to help you work through how we write electron configurations. So in this instance, okay, when you're looking at this particular diagram here, you might notice that along the side there is an arrow that points up with an E next to it. The E is basically telling you that that energy levels are increasing from the bottom to the top, and it stops at 7. And then the other thing that you might notice is there's numbers like 1s or 2s or 2p or 3d or 4f. Those letters are the shape rather of the sublevel or subshell of the energy level. And then lastly, each dash that's represented there represents or can hold a total of 2 electrons. So in the 1s, it can hold 2. In the 2p, there's 3 dashes. 2 plus 2 plus 2 is 6. In the 3d, there's 5 dashes. 2 plus 2 plus 2 plus 2 plus 2 is 10. And in the 4f, there are 7 dashes, and I think you get the idea, hopefully. Now, when we write electron configurations, they will oftentimes look like this. And when we write them, all of these numbers and letters here are codes that tell us very specific information about the location of an electron around the nucleus of the atom. So, the big numbers, the 1, the 2, and the 2 in this case, are the energy levels. The letters, which are all lowercase, the S, and the P, are the shape. And then the superscript numbers, so this one, and this one, are the electrons. Okay? So that's when we write something that we refer to as the electron configuration. Another way that we can represent this, and the way what I'm going to show you next is the exact same element, is called the orbital notation. And it's the same thing, but it's just represented differently. So in this instance, again, I have the large numbers, which are your energy levels. I have the lowercase letters, which are the shape. I have these arrows, which are our individual electrons. And the major thing that's different here is these dashes, and the dashes are orientation in three-dimensional space. Orientation in three-dimensional space. Both of the ways, so both orbital notation and electron configuration are ways that we can communicate where electrons are located around the nucleus of an atom. Now, another set of definitions, I suppose, for lack of a better term, has to do with something that we call valence electrons. Okay? Now, valence electrons are the electrons that happen to be located in the outermost energy level of an atom. Now, the best way for me to try to help you describe that or to see that would be if I draw a picture. So I'm going to have my nucleus here, okay? And then around my nucleus, I'm going to put rings, which are going to represent individual energy levels. And then I'm going to put some electrons on individual energy levels. So I'm going to put 2 here. I'm going to put like 8 here. And there's a reason for that. And then I'm going to put like 2 here. Now, with this drawing, it might be pretty easy to identify the actual number of valence electrons because it's the electrons that are on the energy level furthest away from the nucleus of the atom. So in this case, you might identify that there are 2 valence electrons. The highest or greatest number of valence electrons that an element can have is 8. Now, all of the electrons that are not in the outermost energy level or that are in energy levels that are lower than that, so basically I'm referring to these electrons here, all of those electrons are called core electrons. And if I count up the core electrons, there's 8 in the second ring and 2 in the first ring, so that gives me 10 core electrons. Okay, so now we've got core electrons and we've got valence electrons. And at some point, you're going to have to know how to identify both of those. So now we have enough information that will allow us to start writing something that we call electron configurations or orbital notations. So we're going to start with an element, hydrogen. And if you haven't done so already, you might want to get out your best chemistry friend, your periodic table. Remember, mine's name is Jethro.
Oh, yeah.
And if you haven't done that, or if you are in the process of doing that, or you've already gotten that out, you might identify that hydrogen has how many electrons total? 1. So there's 1 electron in hydrogen. And then what you might want to do is you might want to get out your new chemistry friend. This is Sally, okay? Now, your new chemistry friend always starts in this corner down here. This would be the lower left-hand corner. And it always starts with 1s, no matter what. So when I write the electron configuration, I'm going to write 1s, and since hydrogen is 1 electron, and the S shape can hold 2 total electrons, I'm going to write 1s1. If I'm going to draw the orbital notation, it's going to be very similar. It's going to be 1s. I'm going to add the orientation, and then I'm going to add an arrow up. And I guess I don't really care if you add an arrow up or an arrow down. It just is that when you have to put two electrons in the same orientation, they need to be opposite of each other. And we'll see some examples of that in a moment. Now, in this example, the number of valence electrons is going to be pretty simple to figure out because there's only one. But really, in reality, the biggest energy level present is the first energy level, and there's one electron in the first energy level. So in both cases, hydrogen has one valence electron. The next example that we are going to try is, we're just going to really ratchet up the pressure here, helium. Helium has how many electrons?
2.
Helium does have 2 electrons. So again, I'm going to get my chemistry friend Sally here, and I'm going to start in the lower left-hand corner. And when I start in the lower left-hand corner, I start with 1s again. So it's going to be 1s, and the S shape can hold 2 electrons, so I'm going to put a 2 here. Now the orbital notation will be very similar. 1s, going to add the orientation, but this time I'm going to draw 2 arrows, and one of them is going to go up and the other one is going to go down. Now the reason why one goes up and one goes down has to do with what we refer to as the Pauli exclusion principle, which says 2 electrons in the same orbital, they have to have opposite spin. So that means that if I take 2 electrons and both are negative and they're spinning in the same way, they will repel and not stay there. But if they are spinning in opposite directions, we can get them to stay in that spot. Does that make sense? Question.
How can you tell again the shape, or like if it's going to be an S or P?
So the question is, how can you tell if it's going to be an S or a P? And the actual honest answer is to start anyway. You're going to use this diagram here. Mm-hmm. Okay. So I always start with what's in the lower left-hand corner, 1s.
Oh, the electron capacity. So if it's over 2 electrons, then it'd be.
Yeah.
Yeah.
Yeah. You said P. It would be a P then, right?
Yeah.
But that's not where you start. That's where you end.
Yeah, that's where you.
Okay. All right. So, and we're going to do one like that in a minute, but let's talk about the valence electrons here. So the valence electrons here, the biggest energy level for helium is 1, so that tells me that there's going to be 2 valence electrons. Okay. The next one that we are going to do, we are going to do the element carbon. How many electrons does carbon have?
6.
Yep, carbon has 6 total electrons. So just like before, we're going to use our new chemistry friend Sally, and we're going to start in the lower left-hand corner, and the lower left-hand corner starts with 1s. And the S can hold how many electrons? 2. So I'm going to put a 1s2. And then after 1s, according to Sally, comes what?
3s.
Not 3s.
2p.
You're getting warmer. Not 2p.
2s.
2s, right? Because that's the next thing that comes. So it's going to be 2s, and the S can hold 2 electrons, so I'm going to put 2 of them in there. After 2s, what comes next?
3s.
Not 3s. 2p.
Oh, I see.
So as we are moving up each spot here, we are looking all the way across, and as the things that, like, the next thing would be like 2p, and then it'd be 3s, and then it'd be 3p, and then it'd be 4s, and then it'd be 3d. Do you see that? and then it'd be 4p and 6s. Okay? Now, how many electrons can the p shape hold? 6. And some people want to just put like 2p6. Don't write that because that's not right. It would be 2p2 because 1s2 plus 2s2 plus 2p2 is 6. Okay? Now, when I write the orbital notation, it's a little bit different. It's going to be 1s, and I'm going to add my orientation bar, and then I'm going to do arrow up, arrow down. It's going to be 2s with an orientation bar, and that too is going to be an arrow up, arrow down. Now, 2p hold on. Now, the 2p, we've already said, can hold 6 electrons, right? And if it can hold 6 electrons, that's great, but it has 3 orientations. So I purchased a really expensive model kit to help illustrate that. And they sent me a pen and some paper. So here's the thing. I have my x-axis, I have my y-axis, and I have my z-axis, right? Or my x-plane, my y-plane, and my z-plane. Do you see that?
Yeah.
Okay. Now, the p orbital or the p shape has 3 different orientations, the x, the y, and the z orientation, which is why I wrote 2p, 2p, 2p. Now, each orientation can hold 2 total electrons, but one of the rules, the Pauli exclusion principle rule, let me get it back up here so I can read it exactly verbatim, says if 2 electrons are in the same orbital, they have to have opposite spins. That's the Pauli exclusion principle, so that's why 1s arrow up, arrow down, 2s arrow up, arrow down. Hund's rule says within each shape, there must be an electron in each orientation before a second electron can be added. So what that looks like over here is this, arrow up, arrow up. Now, what is the biggest energy level here? The biggest energy level is 2, and it happens to show up 2 times. So how many electrons are in the biggest energy level?
2.
Plus
4.
2 plus 2, right, would give me 4.
Yeah.
Okay. Questions about this so far? All right. Now. Okay. So the next one that we're going to try is sodium. How many electrons does the sodium have? 11. Thank you. Now, again, I'm going to go grab Sally here, and I'm going to start with 1s, right? Just like we've been doing. So I'm going to start with 1s, and that's going to get the S shape can hold 2. Then I'm going to go to 2s, which can also hold 2. And then I'm going to go to 2p, which can definitely hold 6. So I'm going to do that right away. Now, yes, but so at this point, I've used 2 electrons in the first energy level, 2 electrons in the 2s energy level, and 6 electrons in the 2p energy level. So I've used 2 plus 2 plus 6, which is 10. I have 11 electrons to place, which means I have to go to the next energy level. And in this case, the next energy level is going to be the 3, and the shape is going to be S. And the number of electrons that the S can hold is 2, but I only have 1 more, so I'm going to write 3s1. Now my orbital notation is going to look very, very similar, but it's going to start with 1s. I'm going to have my orientation bar, and I'm going to add an arrow up and an arrow down. 1, 2. I'm going to go to 2s, add the orientation bar, and I'm going to have arrow up, arrow down, 2. Now the 2p, because it has 3 orientations. Now watch how I do this, please. I know it holds 6. I do know that. But I'm going to go and place them individually first. Arrow up, arrow up, arrow up. Then I'm going to go arrow down, arrow down, arrow down. Now the reason why is because we want to take, in the event that we don't fill up the 2p, we want all of the 2p's to have at least 1 electron in them before we double them up. And then lastly, this will be 3s. And it's just going to be an arrow up. So again, going back to that, I'd like to point out, like if you and your siblings ever like get into an argument, your mom or your dad might send one of you to like your room and another one of you to another room and another one of you to another room, right? And if there happens to be a 4th sibling and you've run out of rooms, they'll take that first sibling and put it into one of the rooms with you, maybe. Like imagine that anyway. Okay? And that's kind of how this works. You want to keep the negativity separated before you have to double it up. Now, valence electrons here. Biggest energy level?
Big.
Nope.
Yeah.
Nope.
Isn't it?
The biggest energy level is the 3rd one.
Oh.
So it has 1 valence electron. You thought I was wrong. All right. Woo! All right, here we go. We have entered into the U-try portion of today's lesson. Yeah, the U-try portion of today's lesson. The U-try portion is going to be titanium. How many electrons does the titanium have? It does have 22. So go ahead and give this one the old GHS try. Okay, so you should have hopefully come up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. When you draw the orbital notation, it was 1s arrow up, arrow down, 2s arrow up, arrow down, 2p, 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 arrow up, 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 and then down, down, down. 3s arrow up, arrow down, 3p arrow up, 3p arrow up, 3p arrow up, down, down, down. 4s arrow up, arrow down, and then 3d arrow up, 3d arrow up. And I needed to leave the 3d, 3d, 3d open. Now, the reason for that is how many electrons can the D shape hold? 10. And there's 5 orientations for the 3D, which is why I have written 3D, 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 3D. Okay? Now, the other thing that's important to understand about that is like, if your like older sibling has moved out, their room doesn't just like disappear from your house, even though your mom might like close the door and not let anybody go back in there because they lost their baby. You know, no. So even though somebody might have moved out of your house, right? Like that room is still there. So you still have to have 3D, 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 okay? And the electrons have to be spread out.
So you can't just do up arrow, down arrow, and then leave both of those blank?
The question was, you can't just do up, down, and then leave the 4 3Ds blank, and the answer to that question is no. You cannot.
You gotta spread them out.
You got to spread them out. All right, we're going to try another U-try. Oh, wait, before we do that, let's do the valence electrons. What's the biggest energy level here?
3p. No, 4s.
4s is the biggest energy level, so it's going to have two valence electrons. We're going to do another U-try, which is manganese. Manganese has how many electrons? 25. So you go ahead and give this one a shot. All right, so for manganese with 25 electrons, you should have come up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5 for the electron configuration. For the orbital notation, it's 1s, arrow up, arrow down, 2s, arrow up, arrow down, 2p, arrow up, arrow up, arrow up, arrow down, arrow down, arrow down, 3s, arrow up, arrow down, 3p, arrow up, arrow up, arrow up, arrow down, arrow down, arrow down, 4s, arrow up, arrow down, and 3d, arrow up, arrow up, arrow up, arrow up, arrow up. Okay? So and they should have been spread out. They should not have been doubled up. How many valence electrons? Nope. Let's do, what's the biggest number, what's the biggest energy level for manganese? It is the 4s, which means that manganese is going to have two valence electrons. Any questions? All right. Your homework this weekend is the next worksheet in the packet. It is a two-sider. It is worksheet number 5. You have a little bit of time to work on it. I suggest you take advantage of that.